In this video, I will introduce the architecture of the PIC microcontroller and also talk about some of the special function registers and how they can configure the PIC to serve various purposes. To begin, we're going to talk about the PIC16F1719. This is the microcontroller we're going to be using throughout this course, and as you can see here, it is a 40-pin microcontroller that has a parallel dual inline package configuration. One thing that is important to note is how pins are numbered. So you see the notch that we have right here at the top of the PIC, and then the pins are numbered starting at 1 just to the left of the notch all the way to N/2 on the left side. So in this case, N is 40 pins, so we've got 1 through 20 on the left side, and then you take a U-turn, and you've got pins 21 through 40 on the right-hand side. We have on this PIC microcontroller 5 digital ports that can be used as either input or output. Now, each port does not mean just a single pin. In fact, we are using an 8-bit architecture in this PIC, and what that means is that most of our ports are actually 8 different pins that together form a full register that is 8 bits wide. Now, some of these pins cannot be fully used as inputs or outputs, so you do have some limitations. So for example, port A can be used as 8 pins, but we will not be able to use RA6 or RA7 right here, because those are used for the oscillator. The oscillator is the external clock that we are using in this configuration. Now, you can actually run the PIC without an external clock, so in those situations where you're not using an external oscillator, RA6 and RA7, which is port A bits 6 and 7, can be used for inputs and outputs. But since we are using an external oscillator, those bits will not be useful. That does bring up the point of this naming convention. So the bits associated with port A are named RA, the bits associated with port B are named RB, the bits associated with port C, port D, port E, etc. are RC, RD, and RE. And they are numbered starting at 0 all the way up through 7. So the least significant bit of port A is going to be RA0. You see that right here on pin 2. And then if you go on down, you can see the most significant bit would be RA7, which, as we already mentioned, is the same pin that's used by the oscillator. You note down here that port E is not a full 8-bit register. It's only a 4-bit register, and of that only 3 can be used, and that's because pin 1 is RE3, but that is also where the reset button or the master clear lies. So as I had mentioned in lab, you do have a reset switch, and so that is used by the master clear. That allows you to reset your code back to the beginning, and since we are using this in master clear mode, we cannot use it for RE3. So this shows you kind of the pin diagram, the layout. You have VDD and VSS on both sides. That is where 5 volts and ground are applied. And also, in addition to using things as digital input and output ports, meaning you can drive them or read in from external pins, you can also use 28 of these pins in an analog mode. So later on in the course, we're going to talk about analog to digital conversion, and we will be able to put in analog voltages rather than just a strict logic 1 or logic 0 digital voltage. As you may think, because you have so many pins available, you might want to be able to reconfigure some of those pins. Some you might want to use as outputs, so you can control particular outputs, maybe turning on a light, turning on a fan, turning on a motor, those kind of things. And others you might want to configure as inputs, reading from a sensor, reading some data across a serial channel, determining whether a push button is pressed or not. And so we have what are known as GPIO, which is general purpose input-output pins, which means they can be reconfigured as either inputs or outputs. And so if you're not using them as other purposes, and we'll talk later about how some of these pins can be used for other purposes, such as generating a pulse width modulated signal to control a motor. But if you're not using them in those kind of configurations, you can more generally just set them up as a digital input or a digital output. A general rule of thumb here, and we'll see why a little bit later on in this slide set, is if you're not using a particular pin, we want to make it an input. This is largely because when a pin is set up as an input, it becomes a high impedance pin, which means it does not interfere with any other device that may be accidentally or purposely connected to it. And so if you don't want a pin to have the opportunity to interfere with some other connections, when you didn't mean to do so, it is a good rule of thumb to make anything that you're not using specifically as an output into an input. Analog inputs are generally used in the digital mode. We will only make things analog if we actually need to have an analog input. But so anything that can be used in an analog mode, unless you need it to be used in analog mode, we're going to configure it for digital. And we'll talk a little bit later on in this slide set about how to determine whether a pin is analog or digital and whether it's used as input or output. If you look at Table 2 in the PIC datasheet, you can find some information about what each of these pins can be used for. In the far left column, you see their digital port names, so port A, bit 0, RA0, port A, bit 1, RA1, and you see which pin they occupy on the parallel dual inline package chip. Now, we happen to be using the PDIP configuration, but the microcontroller that we have can actually come in a variety of other configurations. So if you happen to have it in a different packaging, these are the pin numbers there. Since we're not going to be using that, I didn't really highlight that. This ADC column also shows you which of these pins can be used in an analog mode. So RA0 can be used as a digital input or output, but it can also be used as analog number 0. Likewise, analog number 1 is on the same pin as RA1, etc. And as we had mentioned here, RA6 and RA7 is where that oscillator is connected to. There's several other things that you can see on here. I'm not going to elaborate on them right now. So for example, some pins can be used by the USART, which is used for serial communication. We've got PWM, which can be used to drive a motor. You can use things for some timing. You can do some digital and analog conversion, all those kind of things. But for right now, we're just going to focus on analog and digital, and also looking at just the basic input and output structure. And we'll expand on some other features as we go through the course. One thing to understand, again, I like to incorporate a little bit of the history of where we got to where we are now, is dating back to the 1940s, there was a need to add memory to computing systems. And depending upon what type of a system you had, that memory was configured in different ways and in different architectures. And so there was the Princeton architecture, also known as the von Neumann architecture, which was popular in early machines, and then the Harvard architecture became popular in the 1970s onward. And so what's the real difference? Well, with the Princeton architecture, that is the early architecture, all of your memory was in a common block. And so variable declarations, things that were stored for files, some data, all those kind of things were all in one just general purpose memory block. The Harvard architecture actually uses different memory for different purposes. So that is what we have in modern day computing systems. That's why we have RAM, which is a high-speed memory, and then we also have hard disk, which is a little bit slower speed. You might have double EEPROM, flash memory, all those kind of things, and they are divided out for different purposes. And so most modern systems, and our PIC is no exception to that, use a Harvard architecture rather than a Princeton architecture. These were, of course, named after the universities that they were originally researched and discovered. The basic block diagram of the PIC 16F1719 showcases the basic inputs and outputs we have here. Here's our port A through port E. We also have some comparators. We've got some timers. We can do pulse width modulation. There's actually some built-in op amps for doing some analog manipulation there. And then we've got analog to digital conversion. and we will talk more about these as we go on through the course. So just wanted to showcase that to you. At the main brain here is the central processing unit, or CPU, and that determines, based upon all these things on the bus, where data is going, where data is coming from. We also have our program memory. So our program memory stores all of our code in machine code into specific blocks in memory. The CPU actually pulls in the current line of code and executes things in sequential order. And then over here we have our clocks, and we have our master clear, which allows us to reset the CPU back to its default setting, back to the beginning of executing the first line of code that is programmed to it. Here gets into a little bit more of the block diagram. You can see in this slide the different types of memory. So flash memory is used to store your program. That is good for this purpose because it's fairly quick to write, but it is non-volatile memory. It is not as fast to write to flash as it is to write to RAM, but it is non-volatile. So if you turn the power off to your trainer board and then turn the power back on, you will notice that it's effectively the same thing as pushing the master clear. The contents in the flash memory are maintained, and that means your code will be able to keep running even if you disconnect power from your board. RAM is where we store things like our variables. Our special function registers can actually store some values in RAM. We've got a stack, and what the stack is used for is when you are calling a subroutine. We'll talk more about that later, but effectively what it does is it stores the current address of where you're reading from. That's in the instruction register. It stores that, and so that way if you call a subroutine, you execute all of the lines in that subroutine, and you want to come back, you can actually pop the latest address off of the stack, and that will allow you to return back. So when we start talking about subroutines, we're going to see a little bit more about how this stack works. And we have a 16 level stack, which allows us to store the addresses of up to 16 different commands, which means we can call a function or a subroutine, and then within that function or subroutine we can then call another one, call another one, call another one, and we can do that up to 16 layers deep. We also see the use of a multiplexer, which allows us to choose from some other registers. You've got multiplexers that allow you to choose what's happening over here on the ALU, which is the arithmetic logic unit. And then we've got another register, the W register, which we'll talk about in just a moment. So what I want to do is introduce the registers that we have inside of the PIC microcontroller. Registers are the basic building block for everything that we're going to talk about in the context of microcontrollers and microprocessors, and they serve a variety of purposes. Some of them will determine how the chip will function. So for example, there are registers that determine whether a pin is going to be used for analog mode or digital mode. There's another register that determines whether it's going to be input or output. There are some registers that determine whether you're generating a pulse width modulated signal or whether you're doing a timer operation, those kind of things. Some tell us what has happened. So if there was an error, there was an overflow, the status register will give us some information about that. If serial communication is enabled and you have a packet of data that's come across a serial channel and it's now ready to be read, the specific registers associated with that can tell us, hey, there's some serial data now available to be read. It can also track where we are in code in case of the program counter, and it can keep track of the results from operations. So if you've completed an analog to digital conversion and you want to know what the digital representation is for a corresponding analog signal, you can pull that from the registers associated with the analog to digital conversion. We're going to get into much more detail about a lot of the different registers as we go on through the course. Today I'm just going to introduce some of the basic registers that you're going to be using throughout the course and showcase what they are able to do. Registers are actually organized into 32 different banks. What that means is if you are trying to set up specific registers, you need to know where in memory it's located, and you're actually changing some of the addressing when you switch banks. So we're going to talk about the need to switch banks a little bit later on when we get into some example code. But just know that in order to access certain registers, you need to be in a specific bank. There are 12 core registers that are always available in every single bank, and then specific registers beyond that are available in other banks. So let's go ahead and start talking about some of the important registers. The first register to know is the W register, or WReg, and that is short for the working register. If you use some different processors, different microcontrollers, they might call this an accumulator. And effectively, you can think of the W register as what you see on the display on a calculator. So as you're adding up, let's say, a series of numbers, you might add 1 plus 5 plus 7 plus 9 plus 13. You're going to see intermediate calculations on that display. Ultimately, at the end, you only care about the final total, but at every iteration through, adding the next number, the next number, the next number, the display has been updated with the current working total. And so that's how I like to think about the working register, the W register, as it being basically the display on a calculator that can keep track of mathematical operations. So that is one major purpose of the W register, is to track the results of some mathematical operations. You can also have it track logical operations and do some other things like loading a value which will then be used to store into a particular register. This is a core register and will be available in all of the banks on the microcontroller. The BSR, which is short for Bank Select Register, allows us to change from one bank to the other. So if you're trying to, let's say, access the value that is in a particular register, you can copy that register into the W register, which is then available in all of the banks, and then shift into another bank using the BSR, and then store the contents of the one register that's now been copied into W into another register. And there will be some bank changes that will need to occur throughout that process. We're going to see some more examples of this once we start writing some code, but I just want you to be aware at this point that you will need to change banks, and the BSR register is how you do that. In order to actually get all the way through using different registers, we need to have this accessible in all banks. So BSR is actually a core register which will be available in all of the banks of the microcontroller. The program counter, as I'd already mentioned, keeps track of what line of code you're currently executing, and so it can track up to 16,384 commands. It has memory location 0 all the way up through 3 FFF hex. It is a 15-bit counter, so one of the bits is unread, but the other 15 bits, it's actually spread across two 8-bit registers, and that actually allows the addressing of 32,768 instructions. The lower 8 bits can be read in the PCL, which is short for Program Counter Latch, or Program Counter Lower Byte, and then the upper is in the PCLATH. So those are not directly readable, but you can write to the PCLATH. So PCL and PCLATH are both core registers available across all of the banks. The status register is, I would say, beyond the W register, the second most important register in the PIC microcontroller, because this is what tells us what happened after certain operations. So you have a C bit and a DC bit in there. The C bit tells us when there was a carry. So if you happen to be adding some values and it doesn't fit within the 8 bits of the sum, then the C bit indicates that there was a carry out. So with 8 bits, you can represent values between 0 and 255. And if you're adding values and the sum becomes greater than 255, you're going to see the C bit set to indicate that there was a carry out, basically an overflow of the operation. DC is very similar, but you can think about DC as a digit carry. It's not indicating that the entire value in the 8-bit register overflowed, but that there was a carry at the end of the most significant nibble into the next nibble. Effectively, if you think about doing binary addition and adding two binary values together, The DC shows that there's a carry from one 4-bit cluster to the next 4-bit cluster. The Z bit is going to be very important as part of the status register, because that's going to tell us if something went to 0 or not, which we can actually use to check for equality. The status register, being so important, is also a core register available across all banks. So you may be wondering, how do we actually use the general purpose input and output, and how do we actually configure it? Well, we'll talk about that over the next few slides. So I had already mentioned that there are 36 total general purpose input-output ports, or output pins, spread across 5 ports that are 8-bit groupings: port A, port B, up through port D and E, and that the naming convention is R, the letter of the port, and then the number 0 through 7. Ports can be operated in a digital or analog mode, and even within a particular port, let's say port A, you don't have to make all of those pins inputs or all of those pins outputs. You don't have to make all of those pins analog or all of those pins digital. You can, because they're nice and general purpose, you can mix and match. So you could make RA0 through RA3 all inputs, and then make RA4 and RA5 outputs if you wanted to do that. You could make RA0 operate in the analog mode, and you could make RA2 operate in the digital mode. And so you've got a lot of flexibility about what each pin is going to be used for. In general, again, if any of those pins are not being used, it's a good idea to make them inputs so they go into this high impedance state, and we'll see that illustrated in just a couple slides as to why that's important. And so you can use several registers to access those ports and to configure them. So the first registers that I want to talk about are the port registers. I have just the X there as a placeholder because this information applies to port A, port B, port C, all the way up through port E. So you can read from or write to those values depending upon whether you have set them up as input or output. So one of the things you want to make sure you've done is properly set up things as inputs or outputs first, and then you can read from or write to those particular pins using the corresponding port register. So if you want to read in from a switch or a sensor, you want to make things input. If you want to write out to, say, turn on a light, turn on a motor, you're going to want to configure those things as outputs. The port registers do not configure as inputs or outputs. We'll talk about that register in just a moment. But what they do is allow you to set up a specific value. So if you've already made a pin an output, then you can actually set it or clear it to drive that particular pin to 0 or 1. To read from an input pin or drive an output, you have to configure it using the corresponding tris registers, which we will talk about in a little bit. Port A through port E are accessible in bank 0. So if you're trying to access those registers, make sure that the PIC is in bank 0. Latch is corresponding with the port A through port E, and the X here, of course, also follows the A through E. And so this is short for latch. The input and output logic is based upon a digital latch, based upon a D flip-flop. And so this is what allows us to actually read the current value coming out of that flip-flop, which likely, if things are an output, is exactly the same as what should be coming out of the latest port update. But if things are inputs, this allows us to access some things directly off the flip-flop without having to worry about whether the proper output is coming. This will make a little bit more sense once you look at the actual schematic of things in a slide or two. So this is useful if you want to manipulate the current port value by replacing it. So maybe you've got a formula that you want to drive the port value to, and you want to base it on, in part, the current port value. Then you can actually use the latch in that logic. So take what's on the latch and AND it, OR it, add a value to it, and then store it ultimately back out on the port. The tri-state registers, or tris registers, allow us to determine whether something is input or output. If it's output, then that means you can drive that pin directly to a 0 or 1. If it's input, it assumes a high impedance state and only is passively looking at what may be coming on that pin at any given time. So in order to make something an input, you set it to a 1. If you want to make an output, then you clear it to a 0. The way that I remember that is that O and 0 look a lot alike, and so 0 is what makes things output. And 1 and I look a lot alike, so 1 is for input. That's the rule of thumb that I keep in my head as I'm trying to remember, wait a second, in the tris register, do I put a 1 or do I put a 0 whenever I want to set something as an input or an output? But that's my general rule of thumb for remembering those. Keep in mind that bits 6 and 7 on port A are dedicated to the external clock, that oscillator, so you'll want to always make those inputs. Similarly, bit 3 is dedicated to the master clear. You're going to want to set that as an input. You don't necessarily have to. Once the configuration is actually made, it does override anything that you would put as the user of this, so those will actually be set up in configuration bits as to whether you're using the master clear, whether you're using external clock. But it's just a good practice when you're writing code and setting things up that you don't write things to the tris registers that would be contradictory to how those pins are actually behaving. Looking into the analog select registers or ANSEL registers, that allows us to determine whether a particular pin is used in analog or in digital mode. So if you want to do some analog to digital conversion, you would need to set up the corresponding pin as a digital input, and then you can set the corresponding value in the ANSEL register to make things an analog input. So if you want to make it digital, you have to clear or make 0 the corresponding bit in ANSEL X. So that could be ANSEL A if it's a pin associated with port A. It could be ANSEL B if it's a pin associated with port B, etc. So if you want to use things in digital mode, which is what we're going to do in the beginning part of the course, then you need to clear things to 0. If you're trying to use things in analog to digital mode, you need to make sure you put a 1 in the corresponding pin, and that will allow you to do some analog to digital conversion. Not all pins can be used in the analog mode, so it's important if you want to do some analog to digital conversion. You've got a lot available to you, but you're going to want to see table 2 on page 8 in the data sheet, which will allow you to know which pins can be used as analog and which ones are digital only. Alright, so here's an example. If you wanted to use RA0 as an analog input, you would set tris A bit 0, so that's going to make it an input, and then you would also set the ANSEL A bit 0. That should say ANSEL A, not just ANSEL, and then set that so that way it's saying it's in analog mode and it's an input. Here is the generic block diagram for how these ports work. So the main building block for every pin is a D flip-flop or a latch. So right here, if you remember from the previous course, your D is your data coming in, your Q is the current output. Notice right here you've got a tri-state buffer, hence the tris register. If this is a logic 0, then that means your Q is connected right here. Logic 0 is going to allow this buffer to turn into a short circuit effectively. That allows the Q to travel right here, which is connected to the input-output pin. So if you have set things up as a digital output, then this behaves like a short circuit. If you're setting things up as an input, now this behaves like a high impedance, and so you have no direct connection between your Q on the output here and your pin. And so you're not getting a direct reading of the latch itself. If you want to read that, even if you are in input mode, then you can actually read from the Latch register. So if this was, say, one of the pins on port A, then you can actually read Lat A, and that will allow you to read things internally, even though they may not be going directly out to the input-output pin. If you're operating in analog mode, then that means you need to put a corresponding 1 right here, which means that you do not have direct access out here to some of the data bus and things like that if you're reading things and you're in analog mode. So if you have a 0 right here, then your I/O pin is directly connected, so that's in the all digital mode. You're pulling in the I/O pin, and then you have this buffer. If you're trying to read from a port, you set this right here, and that allows the current value of the pin to go back into D, or onto a data bus to be written somewhere else. We'll talk later in the course. We'll have a whole lecture on analog to digital conversion. I just want you to be aware that there are specific registers associated with that. ADCON 0 and ADCON 1 are used for the analog to digital configuration, and as is ADCON 2, and then the results are actually stored across two registers, ADRESL and ADRESH. So we will not be using that for the first several labs, but then we'll get into analog to digital conversion several weeks in, and you'll get a lot of practice. So at first we're going to set all things as digital, but as we start using analog, we're going to pick and choose as to where we're going to put the analog inputs and use them accordingly. So just to get an idea of the bank organization, if you read through the data sheet, there's several pages that are associated with this, 28, 32, 34, and 36. They showcase the 12 core registers that are included here. These are specific registers that are available in all of them. We didn't talk about 7 others, but you can actually see them in table 3-2. And then keep in mind of some of these commonly used. The port registers are available in bank 0. The tri-state registers are available in bank 1. The latch registers available in bank 2, and the analog select registers are available in bank 3. Those are the main registers that you're going to need to be working with for the first couple weeks. But I just wanted to introduce those, and you can look in the data sheet to find out much more about each of those specific registers. So in summary, you've been introduced to several special function registers. You've seen the architecture of the PIC, and that was just a lot of information in one lecture. So that's the benefit of this being recorded, is you can go back if there was anything that was not clear, rewind it, play it back again. And I fully understand that it may be overwhelming at first when you're learning about all these things, but as the course unfolds, you can get a lot more practice working with them. You'll really start to grasp what those registers are used for. And so the best way that I can teach you that is to have you get in the lab, use your trainer kits, and start practicing writing some code and understanding what those different registers do for you. So in the next lab, we will certainly do just that. You'll have the opportunity to write a little bit of code and see what some of these specific registers do when they're actually in practice in a working trainer kit.